Welcome again, and today we will learn about a special type of binary tree named as expression tree. And you can see all non-leaf nodes are operators and leaf nodes are operands. So this kind of tree is named as expression tree, and you can see it is a binary tree because each node has maximum 2 children. So this is a binary tree, and a node may have only one child if the operator is unary. Here, because all operators are binary operator, so um, all node have 2 children. So suppose we have this kind of expression, mathematical expression, and uh, this tree is representing this expression. So if we traverse this tree in order form, we will get this kind of A plus B multiplied by C, and then the plus, and then we will move to the left side, D multiply E plus F multiply G. So this is something in order expression, and you can see here without parenthesis it is difficult to understand the if we want to evaluate this kind of expression, it will be confusing. So if you want to put parentheses like this one, then we can we can modify in order function. You can see in our original in order function we have recursion, base case, and then in order left tree, print out, and in order right tree, and this function is called again and again until we reach the null pointer. So if we want to put parenthesis, we can print this parenthesis before tree node to left. This is something outer parenthesis, and here before printing a node we can add parenthesis here. So it means closing parenthesis. So opening parenthesis, closing parenthesis. So that mean left, and here then we have operator, and then right tree. So this way we can insert parentheses, and if we do, then we can get the results like this one. That means BC is evaluated first, and then the result is added to A, and then the whole result will be added with first we will multiply D and E, and then we will plus it with F, and then we will multiply with G, and this tree and this tree will be added. So you can modify your program in order traversal function, and you can put parentheses for printing purpose. Once we have this tree, it is very easy that we can convert it into postfix form just by traversing it post order way. So this way, this is something post order postfix form. So postfix form is very easy to obtain through the if we have expression tree. Just postfix traversal. Similarly, we can get the pre-order pre-order traversal, and the resultant string will be uh, a prefix form. So it is very easy to convert from one form to another form. If we have just expression, we can just get different forms. So let's talk about how can we construct this expression tree. First, suppose we have an expression in postfix form, and then the algorithm from this postfix form to create an expression tree will be having these steps, three steps. So read a symbol from the postfix expression. If symbol is an operand, put it in a one node tree and push it on a stack. So that means if symbol is operand, we will make a node and then push this node onto a stack. If symbol is an operator, then we will pop two trees from the stack. That means two nodes. Form a new tree, and then we will make a new tree with the operator as the root node and T1 T2 as left and right children's, or left and right subtrees, and then the whole tree will be pushed on back onto the stack. So this is a very simple algorithm if we want to create an expression tree using a postfix form. That means input is a postfix form. So if your input is in infix form or prefix form, then your algorithm will change, and you will write the algorithms and codes for other two types as an exercise. So let's um, see a demo for this um, uh, constructing of expression tree. Suppose we have a stack and we are given a postfix expression. This expression is in a postfix form. So we will read one by one uh, character from this expression. And suppose we have A, B, C, D. These are operands, and we suppose they are all from 0 to 9. They are not in double figure. So we will read first A, and then we will see if symbol is an operand. That means A is a operand. We will make a node, and this node is pushed on the stack. Then we will read next character. It is again a symbol, so we will make a node and push to the stack. So then next character we will see this is not an operand, it is an operator. So what we will do, if a symbol is an operator, pop two trees. That means in the previous we have these two trees consisting just one node, but it doesn't matter. This is something root node for tree T1, and this is root node for tree T2. So if symbol is an operator, pop two trees from the stack. This is something one tree, and this is the second tree, and make a new tree. And we form with this new tree, and operator that was we obtained from the expression is the root node. This operator is root node, and T1 and T2 as left and right subtree. So this is T1 A, and B node is a T2, and then this tree is again pushed to the stack. Then C, D, E are operands, and we made nodes and pushed on to the stacks. And then when we reached at plus operator, so then we have taken out two. Here was D and here was E, so we have taken T1, T2, that means a subtree, left subtree, right subtree, and made plus as a root node, and then this small tree again pushed back to the, and then again we have an operator, so we will take out this one is whole is a T2 and this is T1, and this is the operator, so we made as a root node this operator and left tree, and then the whole right tree T2, and then pushed back to the stack. And now we again have operator and we have two trees, and we combine these two trees using as a left T1 left tree and T2 right tree, and root node is the operator. So this is the way that we can construct the um, the tree. So let's now implement um, this expression tree. So we already have binary tree implemented, and I showed you a few of the functions last time, and I hope you have completed this tree as binary tree. So, and this is our binary node. Mm. So both are templates. So uh, our expression T may looks like this one. We may have constructor and built tree postfix, built tree prefix. That means we are given an array of characters, and we will get a tree. This is something root node of the tree is returned. Root node of the tree is returned, and we specify here instead of t, we specify here type char. So we have three functions. If we are given a postfix form, we can build tree using this function build tree postfix. If we are given a prefix form expression, we can use this function, and if we are given infix form, we can use this function to build expression tree. And all these three functions are returning root nodes of the trees. And then you can see we can evaluate. Already you know how to evaluate a postfix form or infix form or prefix form. In this case, you need just one function. In any, if you are given any type of form, or in any form of the expression, you just need to build tree. If you have tree, you can use evaluate. So all evaluate functions will provide you they will return integer value. That means they will compute, evaluate and compute the value and return you. So here the two functions evaluate without any argument and evaluate binary node of type char, pointer is provided um, as an argument. So these two functions using the recursion to compute the to evaluate the tree, and this function evaluate with stack is not using recursion. Actually it is also a recursion, but we are using stack, and this is something, in this case a system stack is used. So we can have this kind of um, expression tree, and we can make it a subtree of a general binary tree, and all the facilities or functions we have developed in the binary tree we can use in expression tree. So Then I have reduced the form. So we have a binary, we need a binary node and then binary tree, and this expression tree will become a subtree. So let's see its implementation. So let's implement this one. So this is our project. Already we have developed the template node node template and binary tree template class, and I have implemented uh, all these functions. So let's add a new item, header file, and we name it expression tree. Expression tree, and it. So let me make it little bit bigger. So we can do, if not to define expression tree underscore h, then define expression tree underscore h and end if. So let's write here our class. So we need to include, we will use binary tree header we will include here, and let's class expression tree, and we are making it a subclass and public inheritance binary tree, and we put here we want binary tree of char type. So then also here template class T. So we are going to make a class expression tree template, and this template is also is using inheritance, public inheritance, and the this expression tree is a subclass of binary tree class. So then we can have here, so we do not need any data member here, because for tree we need just address of the root node, and this root node is already defined in binary tree. So we will just have public section and few additional additional um, uh, functionalities we want to add in expression tree, and expression tree can use all functions defined in binary tree. So first one is we need to have constructor. So constructor, basically it is a default constructor because having no input argument. So let me make a function template for this constructor. So we have this tree name, and we need to put colon colon, and this is a this class is a template, and we can call constructor from binary tree. So we can call constructor from binary tree, and this kind of constructor, this is class name, and this is binary tree constructor, and then the body of constructor is empty. So please look at this one. We are specifying the type char, because in expression tree we will have a class of characters. So this is constructor, and we will have binary node pointer, right, of type char. This is the return type, and build expression tree postfix, and this is taking a postfix expression as a, okay, just we can put name so that it may be easy for to understand, easy to understand. So or I can short it, name is too big, build tree postfix. That means if a postfix expression is provided, we will make a tree. Similarly, you can have functions in infix, so in that case your input is infix. Similarly, you may have prefix, and your input will be prefix. So I will implement the postfix form based construction. Rest of these two functions you can implement yourself. So we will have here, and we will so we also need to add these because these are function templates. So here we will write code. So first thing, we need to make a stack. So this binary tree already has included the stack. So this is something already we have done last time. So we need a stack of what type? binary node and the pointer binary node of type char, and we can have stack. And then we also need to declare few binary node of type char t equal to new. So this is we have created one node, and also we need two more, and we will put t1 t2. So this node will be used um, for extracting, for popping out from the pop the node from the stack, and these through two nodes t1 t2 are the will be the root node of left hand subtrees, as we have seen in. So um, let's um, so um, so we are given postfix, so let's use for loop for okay, we can use um, equal to 0 loop I is less than length of this postfix. This is something array of character, and semicolon. Here also we need semicolon I plus plus, and we have this loop. That means we want to read character by character this array and write the. So we will have first one, we have if the symbol is operand, right? So it means we need a if statement. If is operator, and this is something postfix I, that mean the if we are reading a character, and this if this is not operator, so it means we need this boolean function is operator. So we can define here this function is operator. It is a boolean function, and it will take a character C. So this is something a function. We can write here this function. We can make before function name resolution operator, and also because we are going to make a template, so even this there is not any template in this T type. That means we have not any parameter type inside this function, but still we need to do this kind of arrangements as we used to do. So then um, it is a very simple function. We will have if if c equal to plus operator or c equal to minus operator or c equal to multiplication operator or c equal to division or c equal to, we can put this one for power. So if c is any symbol among them plus minus multiplication division and this one is for power, so then return true, otherwise return false. So this is a very simple function. So if the character is operator, then what to do? Then we have a, so this is end of for loop, and this is if this is operator, then what to do? Then we have a pointer t, and we will set data to this pointer. Which one data? Data is this is operand. If not operator, then it is operand, and then we will push this node we have this one, yeah, st there, dot push, and this t is pushed onto the stack. So then else part, else mean if operator, it is not operator, then we will just make a node. So and this node will be yeah, we need to put this one here. We will make a new node each time, right? So we can do here, we can just so we will make a node, and this node will be pushed onto the stack, and if not, then again we will create a node, else we will do these kind of operations. We will create a node, and this node set data same. Actually, I can copy this one. Set data, and then pop two nodes and make a tree. So t1 equal to st dot pop, and pop will not return. Actually, it is something top function that will return the top, and then you can apply pop function to delete this one. Similarly, t2 equal to st dot top and st dot pop. So we need to get the element and then delete the element. So, and then you can see then we will create a tree. So we will make tree. So T is a root node, and this is something set left T1, and so T2 T, and T is set right T2. So this is something the tree we have made, and then make a tree and push tree on the stack. So we are doing three things. We are deleting two nodes and making tree, and then third thing is we are pushing back dot push t. So this is another thing. So end of else part, and end of else part, end of for loop, and here we are here. So here we, at the end there will be only one node in the tree. So then we can have here, we will create another node, and then this is something root node root node. So root node will be st dot top, and then st dot pop we will call. So we will call this one to delete the node, and we will return rn. So this root node is returned back. So this is something that we have completed this function. So let's now test this function. So let me tree data structure test here. So let me add here, instead of binary tree, now we can expression tree. We can include expression tree, and expression tree inside uh, has included the binary tree, so we have no problem to make binary trees. So let's now test the expression tree. Expression tree test here. So we can make expression tree of char type, and we can name it et. So then we can have a binary node of type char, and we want uh, its pointer, root node pointer, new. So then again we need here this one, so we will have. So then et dot set root. So it means we have now made an expression tree, and then we want to call built tree postfix. That this is the function we already have, and here we need to provide some parameter. So postfix, and we can define this postfix here. It is a char postfix equal to some expression. So let's take the same expression. We can have here this one. So we can give, we can have this expression so let's build this solution. So many errors. Expression tree. So this is the problem. Expression tree, and we need to put this one, expression tree. Okay, and again let's build. Okay. What is something expression tree? So what is the problem here? So many errors here. So let me figure out. So one thing is, okay, this is one problem, because we this is return type, right? And this is something, this is the function name, and we put here, that means this is something, our mistake. And here we have not made, okay, it seems all errors have gone. So also, instead of integer, I am using this the one alias for unsigned integers, size underscore t type. So let me build. So this time no error. So then we can just so no problem. So let us add few. Now this tree is built, so we want to um, uh, traverse it in order way, and also we want to traverse it in post order, and we want to post order and pre-order. So different ways we can use, and then each time we can move to the next line. So rebuild it. And we can, oh, so again there is a problem. So let me figure out, we have not, so here we actually we made made a mistake. So um, this is something, this is one node, and we need to get this node, and we will run this build tree postfix function, and then we will set root. So this is the one mistake we did. So a node is created, empty node, and then this node is initialized with the root node, and then this root node is set to the expression tree. So let's build again, and then run it. So you can see now, so uh, we have in order traversal and post order traversal. That means this is a postfix form, infix form, and prefix form. So it is very easy. So you can modify these traversal functions if you want to put parentheses in order and in post order and pre order. It is not difficult to modify these things.